Hi, this lesson is about derivatives and where derivatives do not exist. So let's remember what the definition of the derivative is. So f prime, which is one of the notations we can use for the derivative, f prime is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. So let's practice using that. So here we have a linear function, y is 6x. We know that y and f prime are equivalent. So when I take the derivative of y, that's the same as saying f prime. And that is the limit as h approaches 0 of 6 times x plus h plus 3 minus f of x, which is 6x plus 3. Make sure you put parentheses around it because that minus in front of it belongs to both terms, all divided by h. When you do the distribution of the 6 and the negative, the 6x's will cancel as well as the 3's, and so you're left with just 6h over h. The h's cancel, and so your limit value is just 6. Remember, you can't evaluate a limit by direct substitution if you end up with division by 0, which is what would happen if you applied direct substitution. But when we simplify, that h gets canceled. All right, so let's do another one where we're finding the derivative. And so we want to find the derivative of a function at a given point. So your function is given to be this quadratic function, and the point is at 2, -1. So I'm going to do that right from the beginning. I'm going to replace the x with 2. So instead of x plus h, I'm going to have 2 plus h here when I'm actually using the definition. So that's the work that you see here. And remember, that will be the derivative, which is basically the slope of the function at a particular point. Now, since we're talking about a single point, it's not PQ, it's just at P. So the Q doesn't really have any value here because as your limit approaches 0, as h approaches 0, you're really at a single point. So here's the work when you plug in into the definition. It's 1 minus 1/2 2 plus h squared minus your function at 2, which is this part right here. So we need to expand the 2 plus h squared, which is what you see on this next line, and simplify this part here. So you get 1 minus 2 inside the parentheses. Then when I distribute the negative 1/2, you end up with 1 minus 2 minus 2h minus 1/2 h squared. This 1 minus 2, that's -1. And then continue simplifying, and you end up with what you see on the next line, which is negative 2h minus 1/2 h squared all over h. And if you factor out an h from this numerator, and that will cancel with h in the denominator, you end up with this as your general derivative at 2, -1. But as h approaches 0, that second term goes away, so your limit value at 2, -1 is just -2. And that represents the slope of the tangent line to the curve at that point. Okay, so let's move on to example 3. We want to find a general expression for the slope of the tangent line to the curve of, I'm missing a y here, y equals 1 over x. Then find the slope at each of these values at -1 and at 2. So first we're going to find the general derivative of this function, and then we'll plug in the x values. So remember, by using the definition, you will have the limit as h approaches 0 of 1 over x plus h, so the x gets replaced with x plus h, minus your function, which is 1 over x all over h. Now, here I have the difference of two rational functions, so you need a common denominator. And the common denominator, or the LCD, is the product of the two, x times x plus h, which is what you'll see on the next line. The first expression gets multiplied by x, numerator and denominator, which gives you this. And the second one gets multiplied by x plus h in the numerator and the denominator, giving you what you see here. So now I have a common denominator. So when I rewrite this and distribute this negative across, you'll get x minus h divided by, and then this denominator and this h get merged together. So I get hx times x plus h. And that's because when you divide by h, it's the same as multiplying by 1 over h, so it ends up together in the denominator with what's above. Okay, so when you simplify in the next line, the x's cancel, and you get negative h over hx times x plus h. At this point, the h's will cancel, which is what you see here, and your general derivative is negative 1 over x times x plus h. And then we can apply the limit. So as h approaches 0, this term goes away, and you're left with negative 1 over x squared. So that's your general derivative here, and now you can plug in any value that you want for x as long as it's in the domain, and the derivative exists there. So at negative 1, when you plug that in, you get a derivative value of negative 1, and at 2, you get a derivative value of negative 1/4. Remember, both of those values represent the slope of the tangent line to the curve at that particular value. So let me just draw a graph of 1 over x. 1 over x looks like this, and like this. And so what this is saying is that at negative 1, my slope of a tangent line would be, the slope here would be negative 1. And at negative 2, notice that the slope of the tangent line will be flatter. So here your slope is negative 1/4. So the closer x gets to 0, the sharper the slope of the tangent line is, and the more negative your x value becomes along this side, your slope will get closer to 0 because it will become flatter and flatter. So that's like a graphical representation of what we just talked about, which leads us to the next topic, graphical interpretations of f and f prime. Any function f and its derivative f prime, well, they can be graphed as well as any higher order derivatives. And so just to recall the relationship between f and f prime, for any interval of points on f where the slope of the tangent line to the graph is negative, that will correspond to the graph of f prime where the graph is below the x-axis. Below the x-axis means f prime is negative. So that has to be in sync. If the slope of the tangent line to f is negative, then the graph of f prime must also be negative. Similarly, if the slope of the tangent line to f is positive, then your graph of f prime must be positive, must be above the x-axis. And where the slope of the tangent line is 0, that's where an f prime is 0. So f prime is equal to 0, those would be x-intercepts of f prime. And then again, the same relationship would exist between f prime and f double prime, because f double prime is the derivative of f prime. All right, so let's try to explain that on a graph so that it makes more sense to you. So notice that I've drawn here a graph, f of x, that's in blue. And I have two values represented on this graph at x sub 1 and at x sub 2. And at those 2 points, a tangent line would be horizontal at those 2 points. And horizontal lines have slopes that are equal to 0. So anything before x sub 1, I have a different relationship in terms of slope. Between x sub 1 and x sub 2, there's a different relationship, and then there's a different relationship after x sub 2. So on the interval, so now I'm here reading this, on the interval from negative infinity to x sub 1, so that's this piece over here, and also from x sub 2 to infinity, so this is this piece over here, the slope of the tangent line would be negative. Therefore, f prime is negative. On the interval between x sub 1 and x sub 2, so that's this piece here, that's where the slope of the tangent line would be positive. So f prime is greater than 0. And at x sub 1 and x sub 2, well, f prime of x sub 1 would be 0, as well as f prime of x sub 2, because the slopes of the tangent line there is 0 because they are horizontal. Okay, so let's look at actual graphs of f prime, and f double prime. So f is graphed here in black, f prime is graphed here in red, and f double prime is graphed here in green. All right, so let's talk about the black graph first, the graph of f of x. So anywhere from this point and to the left, the slope of the tangent line here would be positive. So any point along that side, I would have a positive slope of a tangent line. And notice that f prime from this point right here and everything to the left, f prime is also positive. This whole part from here to the left have positive values, not the slope, just the values are positive. Where the tangent line to the graph would be equal to 0, the slope would be equal to 0, well, notice that that's where f prime is also equal to 0. I have another one here where the tangent line would be 0, and notice that that corresponds with this value, which is f prime, and that's equal to 0. So the tangent line relationship has to be the actual value of the corresponding derivative. Okay, so similarly here, if I'm on this piece of the graph, this piece right here, any point on that graph would have a tangent line that is going like this, which means my slope is negative. And notice that on that part, my f prime is also negative. It is below the x-axis, and therefore it has negative values. So that will be consistent throughout. So now let's look at f prime to f double prime. Let me just clean this up so it's easier to read. So f prime is the red graph, f double prime is the green graph. The slope of my tangent line here is 0, and notice that that corresponds with the green line. It has a value of 0. A tangent line to the left of that horizontal line here, this would be negative, and notice that similarly, all of the y values to the left of this parabola are also negative. These all have negative values. But if I'm on the right side of the graph, this has a positive slope, and notice that my line is positive on that side of the graph. So again, this will always be the case no matter what your graphs are. The relationship between f prime, and f double prime, the slope of the tangent line, the sign of the slope of the tangent line has to correspond with the sign of the graph of its derivative. Okay, so let's talk about y equals 1 over x. I talked about it briefly below in the previous couple of minutes, but here I'm going to graph both the function and its derivative. The derivative of 1 over x is negative 1 over x squared. We did that a few minutes ago. So here are the graphs here. I've graphed 1 over x in red, and y prime is in blue, dark blue. So the graph of 1 over x is here. Anything on this side of the graph is going to have a tangent line that is going downward from left to right. The sharpness of the graph will change as you're moving along, but it will always be negative. And the same is true on the other side of 1 over x. This has a negative slope. So does this over here. It's just the sharpness of it will change. But y prime is always negative, which is why the graph, the blue graph, is all below the x-axis. Nothing is above the x-axis. This will never be a positive value. All right, so here we want to find the slope of the tangent line to this square root function, and this is to practice a little bit more of the definition of the derivative using different types of functions. So here, dy dt is another way of saying y prime or f prime. This is the definition of the derivative. You replace your x with, your t with t plus h, and then minus f of t or y, which is square root 4t plus 5 all over h. Now here we have to apply a technique that's used a lot in algebra, which is, in order to simplify this, we're going to multiply by the conjugate of the expression with the radicals. So the conjugate means that it's the same two terms here and there, but a different sign in the middle. So we have a plus in the middle. So in the numerator, you're going to have to FOIL that out because you have basically a binomial times a binomial. So I have two radicals here and two radicals here. One is being subtracted, one is being added. And when you're multiplying conjugates, you really just have to multiply first and last because the outer and inner, when you FOIL, will cancel each other out. So you really just have to do first and last. And that's what you see here. The radicals cancel out. So you have 4 times t plus h plus 5 minus 4t plus 5. Make sure this is within parentheses because that minus belongs to both of them. Then the denominator, all I did was just put these next to each other. You don't distribute the h. That's not necessary. So I get this expression here. Then on top, there's some work to do, some distributing to do, so you end up with this line here. The numerator cancels except for the 4h. And then at this point, the h's cancel, so that h cancels with that h, which avoids that whole issue with division by 0. So at this point, you can apply direct substitution, replace the h with 0, and you end up with the result on the next line, which is 4 over square root of 4t plus h plus square root 4t plus h. Now you can add radicals as long as the inside part or the radicand is the same. So I end up with 4 over 2 square root 4t plus 5, and then 2 goes into 4 twice, and your general derivative is 2 over the square root of 4t plus 5. Then I have to evaluate it at 1. And when you do, you get 2 over root 9, which means that I have a derivative of 2/3. Okay, so this is a slightly different problem, although similar in terms of what the concept is of derivatives. So we want to find the point or points where the slope of a tangent line to the curve of y equals 8x minus x squared has a slope of 6. So I skipped some steps here. I gave you the derivative right from the beginning. So you would have to apply the definition of the derivative, and it would all work out to be 8 minus 2x. What's important here is that you're told that the slope is 6 and the derivative is the slope. So that's the equation you have to set up. set the derivative equal to 6 so that you can then solve for x, and then the x will give you part of the point, and then you can solve for y. So we have 8 minus 2x equals 6. When you solve for x, you get that x is equal to 1. But then you have to find the other half of that point by plugging it into the original function. You substitute 1 in for x, and you get that y is 7. So the point on the curve where the tangent line has a slope of 6 is the point 1, 7. Okay, here's another example. We want to find the derivative by using the definition and then determine the values for which the function is differentiable. So sometimes the derivative does not exist at certain points. We know right from the beginning that this function is undefined at 4, but let's see how the whole thing works out once we find the derivative. So this is another rational function. Here I've applied the definition. So I have the limit as h approaches 0 of 5 times x plus h over x plus h minus 4. So notice that all of the x's get replaced with x plus h. And then it's minus f of x. And f of x is just the function itself. So minus 5x over x minus 4. And then the whole thing is divided by h. Now this is similar to one we did earlier. I need to get a common denominator, and the common denominator is just the product of these two. So the first one, the first rational expression gets multiplied by x minus 4. The second one gets multiplied by x plus h minus 4. And then I'm showing you here that I'm rewriting this divided by h like this, divided by h, so I can show you in more detail what happens with that h. So in the numerator, you have to expand and distribute. And then I also rewrote this divided by h as times 1 over h to show you why that h then ends up getting multiplied by the common denominator. So the numerator, lots of things cancel. You end up with negative 20h over that denominator. At this point, the h's cancel, which is good news because then I can apply direct substitution. So at this point, you can apply direct substitution. So you end up with negative 20 over x minus h to the second power. And that's your general derivative. So just like the original function, this derivative would exist everywhere except at 4, because at 4, you would be dividing by 0. So the function is undefined at 4, and it is differentiable over all real numbers except 4. So it's differentiable from negative infinity to 4 and from 4 to infinity. So derivative does not exist at 4. So let's talk more about that. If f of x is differentiable at some number that I'm saying is a, at x equal to the a, then f of x is continuous at x equal to a. Remember, continuity does not mean that it is differentiable. So you can have a function that's continuous where the derivative does not exist, but what the theorem says is if it is differentiable, then it will also be continuous. Okay, but the reverse is not true. So let's talk about some reasons why some functions are not differentiable, or some locations where they wouldn't be differentiable. So a function is not differentiable at a sharp corner or a kink. So this is a great example of a function that is continuous over all real numbers. It looks like this. So domain is all real numbers, but the derivative does not exist right here at the origin because that's considered to be a corner. So the function absolute value of x, the derivative exists everywhere except at the corner, which is 0. It would also be not differentiable at any discontinuity, which was the example that we did above. It's not continuous at 4. because it doesn't exist there, and therefore derivative does not exist. And this is along the same lines because some discontinuities are where you have vertical tangents, this being one of them. There's a vertical tangent line at 4. And so that's just a more specific example of where if the graph has a vertical tangent line where the function does not exist there, then your derivative would also not be a finite value, would not exist. Okay, so let's move on. If all values of x, identify all values of x where the function is not differentiable in state y. So we have a function here in purple. This has several places where where the derivative would not exist. So it wouldn't exist at -2 right here because that is a corner. It wouldn't exist at 2 because it's a discontinuity and it's actually considered to be a removable discontinuity. And it also would not exist at 4 because that's considered to be an infinite discontinuity. Okay, so that's it for this lesson. Give the homework a try. Good luck.